Good afternoon. I'm Simone Dalle Fabbriche, and this presentation is about my thesis, which is the analysis of the plasma discharge in a radiofrequency ion cluster, and my supervisor are Eduardo and Joey. So first of all, let me introduce a radiofrequency ion cluster. So a radiofrequency ion cluster, let's start from its name. Radiofrequency is referred to the way the plasma is generated and sustained. So we have a main body with a coil wrapped around. We have an oscillatory current in the coil, and we induced electromagnetic field inside the cluster. And in this way, we basically heat up electrons, and we have ionization through electron bombardment. Keep going with the name, is an ion cluster, so it means that we have a set of grids that are electrically biased, and these are used to achieve very high velocity and to extract these ions in an actual way. It's not a new technology. It's one of the most mature technology with all effect thrusters. And especially radiofrequency ion thruster flew on several missions like Eureka and Artemis. Here you have some example. And are also commercialized by some companies like Ariane, Busek, and TrustMe. Why do we study RITs? So first of all, because they are ion thrusters. This means that they have some advantages, especially with respect to all effect thrusters, and the advantage stands in the very high specific impulse and very high velocity that they can achieve. So also the thrust efficiency is high, which makes them one of the best options for scientific missions. However, they have some drawbacks, like the lower thrust to power ratio and the more complex electrical circuit. Radiofrequency ion thrusters in particular have some further advantages that are related to the simpler configuration with respect to classical ion thruster because they don't have an internal cathode. This makes also them it increases the lifetime of this thruster, and they make them very easy to scale, especially scale down to low power case, and they also show good performance with alternative propellants. So here comes the objective of my thesis, which is to model, and in particular to understand the physics that happens inside the radiofrequency ion thruster to improve their performance. And in particular, in my thesis, I'm doing numerical simulations with hybrid codes, which is a mix between peak and fluid codes, with hyphen, which is the code that Iñaki was explaining before, to understand these thrusters. So here we have a sketch of the radiofrequency ion thruster. We can divide the thruster into 4 different parts. We have a discharge chamber, we have the radiofrequency generator, we have the grid system, and then we have the plume. However, the plume is out of my thesis, and if you're interested, there are people in my group that are working on this. So, as you can see, the entire system is quite complex, and simulating the radiofrequency ion thruster all at once is quite complicated. So we want to simplify the problem to better deal with all those different regions. So this is what I did at the beginning of my thesis. We started working on the discharge chamber, and in particular, we decided to simplify the problem avoiding the radiofrequency generators, so the power in those first simulations was assumed to be uniform and constant in time, and we avoided also the acceleration system, including a semi-transparent surface. With this, we decided to do a set of analysis to see the interaction, basically the influence of operative and design conditions on the thruster itself. So we have seen, for example, here the influence of the power, and we have seen very high losses. We have seen a displacement in the plasma bulk, but we also have extended our parametric analysis with changing the chemistry, changing the numerical properties like the transparency of the grids and operative conditions. These results, I presented them last year, so I went very quickly on them, and I also published a paper with these results in 2025. Then, last year, we decided to do another step, which was, okay, let's now avoid the assumption on the uniform power deposition, and let's start to study the radiofrequency generator. So we kept the same domain as before, but we added basically a 1D Maxwell solver to solve a purely axial magnetic field and its implications on the plasma inside the thruster. So this is what we did. Here we have the assumptions that we made. And in particular, with this, we obtained the 1D Maxwell equations that I was saying before with a boundary condition, which is the magnetic field at the maximum radius that is governed by a driving frequency. And we have a consistent power deposition term, which now comes from the azimuthal work of the electric field. So just a comparison in terms of equations between the previous model and new one. We have added the magnetic field, the azimuthal electric field, which in to the axisymmetric code is like was not included before. And we also have to add the electron inertia. So here we have a simulation. So you can see the time evolution of some of the plasma magnitudes in time with respect to the boundary condition that we applied. And we have some periodical oscillations. We have studied also the external radio frequency circuit. In this plot, maybe we can appreciate better the phase shift and everything. Here we have a radial time plot, where time is expressed in radio frequency cycles. And in particular, you can see that in the first three plots in which we have the electromagnetic fields and the azimuthal electric current, we have a sinusoidal behavior with a phase shift, which mainly depends on the electron inertia contribution. We have some variables that are oscillating with twice the driving frequencies, like the positive power and the electron temperature. And we have other variables like the ion electron current that are not variating due to the very large ion inertia. This also applies to the plasma density. One other thing that we discovered is that, well, in a normal configuration, we don't have a magnetic field. We don't have a permanent magnetic field. But we have seen that this oscillatory magnetic field was able to confine the plasma and to produce an electron confinement effect that also has an improvement in the performance, as you can see here from the utilization efficiency and the beam current. This was something that was commented in some papers, but was not identified as we did. Going to the equations, so here you have the time average radial momentum electron equation. And you can see that this one is basically balance between compressing and expanding forces. And you can see that when we moved from the previous model, which is the model without the magnetic field, to the model with the RF magnetic field, we have another term, which is in green, which comes from the Lorentz term, which adds more or less the 25%, which increases of the 25% the total compressing force, which then is the reason why we have this plasma confinement. So this is what we did. Now we are working on a paper, on a journal paper with these results. And these results has also been presented in 2 different conferences. And what's next? Well, we decided to do another step, which is, OK, let's now deal with the semi-transparent surface, and let's try to simulate it in a more proper way. So we decided to move into the acceleration system, and in particular to do ion optics analysis. Ion optics analysis means that we are going to study the way the plasma is, with ions are focused and extracted from the grids. And in particular, we want to study the maximum beam current that we can extract from these grids and the space charge effects. Moreover, in September, I'm going to have my research stay, which is going to be hosted in Bari at the CNR. And in this research stay, the focus is the analysis of air-breathing radiofrequency ion cluster. So air-breathing is nowadays a hot topic, and Andres is going to talk about it later. And that is what we are planning to do in the next few months. So this is a list of the achievements. I attended 3 different conferences, and I published 1 paper, and we are working on another one. And that's all. So if you have any question, I'm here.